Hey guys, welcome back to the LearnAPChem series here at LearnAP. Today, we're going to go over a deeper dive into the atom. So we'll talk about the electromagnetic spectrum, wavelength and frequency, subshells, orbital shapes, quantum numbers, Hund's rule or Hund's bus, orbital box diagrams, the Pauli exclusion principle, photoelectron spectroscopy, electron affinity, electronegativity, and ionization energy, as well as effective nuclear charge. As usual, leave a comment if you're confused or have questions, or you can ask in the weekly live streams we do every Sunday from 5 to 6 p.m. Eastern. Other than that, we'll get started. Alright, so let's start by talking about the electromagnetic spectrum. The electromagnetic spectrum describes a range of all electromagnetic radiation. The spectrum is described according to wavelength and frequency. So if you see over here, we have shorter wavelengths and higher frequency on the left, and the opposite here on the right. Wavelength is the distance between the peaks of the waves and is described in meters or nanometers. Frequency is how often the waves repeat themselves and is described in hertz or the number of cycles per second. So hertz is equivalent to the number of cycles per second. If you're curious as to what wavelength looks like, so if we have some wave here, the distance of this is going to be our wavelength, which is this symbol here, lambda. As you may have already seen, shorter wavelength means higher frequency and energy, and vice versa. So if we have a wave with a shorter wavelength, it's going to have a higher energy and a higher frequency. But if we have a longer wavelength, we're going to have lower frequency and lower energy. So the electromagnetic spectrum includes gamma rays, X-rays, UV rays, visible light, infrared rays, microwaves, radio waves, and long waves. It's just important to know the order of this. So you should know that a long wave has less energy than a UV ray, and so on and so forth. What you should know is that visible light's wavelength is 400 to 700 nanometers. Alright, so let's go over some important formulas you need to know. The first one is lambda V equals C, or lambda is our wavelength and must be described in meters. C is the speed of light, which is approximately 2.998 times 10 to the 8th meters per second. V is our frequency, which must be described in hertz. So that's a pretty straightforward formula. Wavelength times frequency equals the speed of light. Another formula is E equals hV. E is our energy measured in joules. H is Planck's constant, which is approximately 6.626 times 10 to the negative 34th joule seconds. And then again, V is our frequency, and again, should be described in hertz. If you're curious, I can solve this equation up here for V. So C over lambda, and then substitute that in to this bottom equation, and I'll get this, which you may have seen. Alright, so let's talk about writing out electron configurations now. When we're writing out our electron configurations, we want to write the energy level, followed by the shape, followed by the number of electrons in the orbital. So for example, if we wanted to write out an electron configuration for helium, we would write 1s2. So we have this first energy level, followed by the shape, which is always S. You always start with S, followed by the number of electrons in the orbital. So here, for our S orbital, we have 2 electrons. Now, if this is your first time talking about electron configurations, you're probably confused. You probably don't know how to figure this stuff out, and that's perfectly fine. There's an easy way to do this. So the first step is we always start at the first energy level and work our way up. The first energy level only has s orbitals, the second only has s and p, the third only has s, p, and d, and the fourth and greater has s, p, d, and f. Now there's a really easy way to do it, and that's to use the periodic table. So if we go over here, we have our periodic table, and let's pretend that helium is right here. So let's say we wanted to write out our electron configuration. Whoops. I'll zoom that in for you. For magnesium, all we have to do is use this. So here is S, here is D, and here is P. And then these over here are F. And then here are our energy levels. And now all we have to do is work our way across the periodic table until we get to magnesium, starting from the top left and going across like so until we hit. So let's start here. So we have period 1, so we write out 1. And then these two are in the S category, so S2. Now, if we go across, there's nothing left, so let's jump down to the second period, which is our energy level. We jump across here to these two S's, so 2S2. And then if we jump across, we encounter these elements here. And there are 1, 2, 3, 4, 5, 6 of them. And these are in the P category, so 2p6, because we're still in that second energy level. And now if we go across here, we can see that there's nothing left, so let's jump down to the third energy level. And we are in the S category. And right here we hit magnesium. So we're only going to write out these two, and there's our electron configuration using the periodic table. Now there's actually a shorthand way to do this. So we can use noble gases in brackets. So for this, what we would want to do for shorthand is write out the noble gas one period above. So here magnesium is in period 3. Just zoom in on that for you. So it's in period 3, so we're going to write the noble gas in brackets in the period above here, which is neon. So I'll write Ne in brackets, and then I'm just going to jump down and only write out the electrons on this third period right here, because that's where our element is, which would just be 3s2. And these are one and the same. This is sort of a lot to take in, so again, if you have questions, be sure to leave a comment if you're confused. Alright, so let's talk about quantum numbers now. In general, a quantum number is just describing something about the electron. So we'll start with the principal quantum number, n, which describes the energy level of an electron. So you're already familiar with this. N equals 1 is our first energy level, n equals 2 second, etc., etc. If n increases, this is called absorption, and the electron is said to have absorbed photons, which is just a particle of light. If n decreases, this is called emission, and the electron is said to have emitted photons. So you might be asked, like, an electron goes from n equals 4 to n equals 2. Did it emit or absorb photons? And since we're decreasing from 4 to 2, we would have emitted photons. Now we have the orbital angular momentum quantum number, which is denoted as this lowercase l. Describes the shape of the orbit that the electron is in. So L equals 0 describes S, L equals 1 describes P, and so on. So L equals 2 would be D, L equals 3 would be F. We also have the magnetic quantum number, which is M, sub L, and that describes the number of orbitals and their orientation within a subshell. And this can range from +1 to -1. And then finally we have the electron spin quantum number, which is m sub s, and that describes the spin of an electron within a subshell. The value of m sub s is either +1/2 or -1/2. Positive describes the upward spin, and negative describes a downward spin. And we'll talk about m sub s a little more coming up here. Alright, so let's talk about Hund's rule now, or as I like to call it, Hund's bus. So imagine that we're on a bus and it's being driven by Hund. You know, Hund was a chemist at one point, but didn't really work out. He fell on some tough times, and so now he's driving the bus. And so as people get on Hund's bus, they're going to sit in empty rows before they start to double up and sit next to each other. So the same thing goes for electrons in an atom. So let's imagine for a second that we have just these two p orbitals. Normally we have 3, but I can't really draw in 3 dimensions, and that would just confuse people, so we'll just pretend we have 2. Now if we have 2 electrons, they're going to go on different p orbitals separately before they double up. So now if we added a third, they would double up. But if they don't have to, they won't. So that's all that Hund's rule is. So let's talk about orbital box diagrams now. For an orbital box diagram, we're going to draw an arrow pointing either up and down for each electron in the orbital. So one box equals one orbital. A maximum of 2 arrows or electrons can go in each orbital, and the arrows must point in opposite directions. Follow Hund's bus when filling out the diagram. You should also note the Pauli exclusion principle. 2 atoms occupying the same orbital cannot have the same spin. So let's see what this all looks like. So fluorine has 9 electrons. So first we're going to go to the lowest energy level. Here, 1s. And we're going to draw in 2 arrows facing opposite directions, indicating opposite spins. Now, since there's no more room in the 1s orbital, we're going to go up to the 2s orbital. Again, doing the same thing. But again, we still have more electrons. So we're going to move to the 2p orbital. So we have 5 to draw, so here's 1, following Hund's bus, 2, 3, but we still have 2 more, so these are going to double up. And this is our electron orbital box diagram for fluorine. So again, start with the lowest energy level in the lowest subshell, and then move up. Always draw these arrows in opposite directions, which, if you didn't catch, are representing m sub s. Alright, so now let's talk about electron affinity. Electron affinity is the amount of energy released when an electron is added to a neutral atom or molecule in the gaseous state to form a negative ion. This varies diagonally across the periodic table, with fluorine having the lowest and francium having the highest. So we have this diagonal trend right here, meaning that fluorine is releasing the lowest amount of energy when an electron is added to it, and francium having the highest. Similarly, electronegativity describes the attraction of electrons to individual atoms, and this is varying the same as electron affinity. However, fluorine has the highest electronegativity, and francium has the lowest electronegativity. Now let's talk about ionization energy, which is the energy needed to remove an electron from an atom completely. Energy must always be added to remove an electron, and removing the first electron is called the first ionization energy. Removing an atom's valence electrons requires far less energy than removing inner electrons. So if you direct your attention here, we have this table of the ionization energies for different electrons. So non-bolded numbers indicate valence electrons, while bolded numbers indicate inner electrons. So you can see that these non-bolds aren't so high when we compare them to these inner shell energies. Alright, so let's talk about photoelectron spectroscopy. This is where high energy beams are shot at elements and electrons are rejected, and this is called the photoelectric effect. The graph shows how much energy is required to remove electrons from each orbital. From these graphs, we can deduce what the atom is. So if we look here at this photoelectron spectra of nitrogen, we can see that we have this first energy level, and we know that this has to be 1s. So similarly, this must be 2s. And if we look here at the proportion, we know this is 2p. And to determine the number of electrons, we can see that this is going up 2 for each electron. So here we can see that this is 2p3. And if we looked at which atom had this electron configuration, we would see that this is nitrogen. Alright, so now let's talk about effective nuclear charge. And this is also called electron shielding. This describes the net charge of an atom. And so to get our effective nuclear charge, we just do the number of protons minus the number of electrons. So take here, for example, the lithium ion, where we have 3 protons, 3 neutrons. I won't draw them in just because of space, and 2 electrons. If we wanted to get the effective nuclear charge, we do the number of protons, 3, minus the number of electrons, which is 2, and we can see that we would get 1 as our effective nuclear charge, meaning that the net effect of this atom right here is +1. And so that's all that's saying. Alright, so now let's talk about cations versus anions. You may have heard these terms thrown around, and you might be wondering what this means. So we'll start off by saying that an ion is an atom or combination of atoms with a net charge due to the loss or gain of electrons. A cation is an ion with a positive charge, and an anion is an ion with a negative charge. So we can sort of remember this by saying that cations are positive, just like this cute cat shown below. Note that cations are smaller than anions because the protons are pulling the electrons closer to the nucleus, while on an anion we have more electrons that are sort of pushing each other away, and that's going to give us a larger radius. Alright, so that brings me to today's challenge problem. What element is represented by the photoelectron spectra on the right? The solution to this problem is on our website, LearnAPChem. I'll also include a direct link in the description. If you found this video helpful, please like and be sure to subscribe for future content. Like us on Facebook and follow us on Twitter for updates about our new videos and live streams, which we do every Sunday, where we answer your questions about AP Chem. Again, that's going to be from 5 to 6 p.m. Eastern on Sundays. Links for that will also be in the description. Leave a comment if you're still confused about anything, or also any comments on the videos in general. Other than that, I want to thank you guys for watching, and I'll see you in the next video.